Okay, try it now.
Yeah, that looks like it worked. Thank you.
Sorry about that. Okay, try it now. Okay, good morning. Welcome to lecture 10. I want to start out today. I have a couple of announcements or so. Let's jump in. Are there any questions about anything before I start? Okay. So I want to remind you, if you don't have that on your list of pressure topics, that homework 3 is due Friday, tomorrow. And quiz 3 is a week from today on Thursday, March 4th, from 10:45 to 12:05 by submission by 12:35. We will have 2 quiz review sessions again this time. Monday at noon, run by James Fanton. Use his Zoom link and password for the office hours to get to it. And Tuesday at 5, run by Liu Nancy. Use her Zoom link and password for office hours. Let me know if these review sessions are beneficial. We've also been trying to stream them and put them up on YouTube so that people could use them to study from again after the time. Let me know if this is helpful or not. If it's not helpful, we'll try and make changes. Oh, they're super helpful. Good. I'm glad to hear that. That's why we do them. Okay, what else do I want to remind you of? The content for the quiz is the material in sections 3.1 to 3.4. We're covering 3.4 today and doing some review. Looking ahead, if you remember, Friday is a no instruction day university-wide. And on Monday and Tuesday of the following week, the 8th and 9th, is the mini break for this class. Remember, it is not a general university thing, not a general CS thing. It's something that I'm trying to do to give you guys a break to catch up and take a deep breath. There are no lectures, no office hours, no pre-lecture problem sets due on Tuesday. Okay? It's catch-up time. Are the 2 review sessions different in content? I don't know. They're basically, they try and cover, they try and answer whatever questions people ask. So if you're there asking a question and you weren't at the other one, then it'll be different in content because your question will be there. There's always some material that they try and start out with that's the same, and then it goes by way of whatever people ask. So if you're not sure about going, go to both. You're welcome at both. I know it takes time, but if it's helpful, then that's part of your studying. That brings up my next question. As almost mid-semester, I want to take a look and I want you to tell me, I'm going to put out a poll later. I'm going to put out several polls. And I want to know, to get an idea of how much time you guys are spending on this class outside of class hours. And not just a general statement saying, oh, I spend forever on it. I'm trying to figure out how much time do you spend watching the pre-recorded videos? How much time do you spend working on reading the book? How much time do you spend using the pre-lecture problem sets? How much time are you spending on homework? Because I'm trying to see if I need to try and make some mid-semester adjustments that work. So if I'm killing you all, I'd like to know about it. It's not my intent. If a few of you are struggling and spending forever, but most of you are spending what I consider a reasonable amount of time, then maybe we can work with you separately because you're struggling and we need to see what the problems are. You may have separate problems. If nobody's struggling, I can say, whoopee, that's great. Now, if you're not spending as much time as you think you should because you've got so much workload from your other classes, let me know that too. I can't affect them, but I can be sympathetic. So I'm not sure which of these many categories we're fitting into, but I want to try and find out to see if we can make any mid-semester adjustments. Okay? Okay, so good. Shall we begin? Shall we jump in right now? Are there any questions about anything that we have to do now? Quiet. Okay, in that case, I guess it's straightforward, so let's go. Let's do a practice problem. Okay, this is material from, the first lecture, second lecture. So if you have a set 1, 3, 5 with 3 elements and another set B that has 2 elements, the numbers 2 and 4, what is A cross B? So A cross B, remember it's the set of ordered pairs. So it's the set of ordered pair where A is in A and B is in B, A in A, B in B. Well, that's nice. That's theoretical, but I really want to know, what is it? Tell me the numbers. Tell me the pairs. So we have 1, 2, 1, 4, 3, 2, 3, 4, 5, 2, 5, 4. How many elements does it have?
6.
It has 6. So in general, if you have a set A with M elements in it and a set B with N elements, then the number of elements in A cross B is equal to M times N. If you ever can't tell my M's and N's apart, tell me, I'll try and work on it. Okay, so that's it. We've got them all. Now, one of the questions is, well, if you're asked to enumerate, how do you know how to try and list them? Well, it's a set, so the order doesn't matter in general. But when you're listing them, in order to make sure that you've got everything, one of the ways I do it, not required, one of the ways I do it is I take the first element in A and then I pair it with make pairs with all the second elements in B. And then the second element in A and pair that with all the elements in B and so forth. And that way you can be sure that you don't miss them. Now, when I say first element and second element, I mean that when I write the set, I put them in some order. Remember, sets have no order. But when you write them down, you tend to just list the elements in some order or another. So you can use that as making your pairs. Okay? Okay, we have another set of things on that. What's the power set of A cross B? Oh, well, we better rewrite the power, what is A cross B is. A cross B was 1, 2, 1, 4. 3, 2, 3, 4. 5, 2, and 5, 4. Okay, what's the power set? Well, first question is, how many elements is it going to have? That's right. Corey says 2 to the 6th, and he's absolutely right. Remember, the number of elements in the power set is 2 to the number of elements in the set. So what are the elements of it? Well, the way I list them, again, not required, but it's a lot easier to do it this way than it is for me to just randomly pick things. I take the empty set and the whole set, which is A cross B. So those are 2 elements that I know are there. They're subsets of the set A cross B. And then I start enumerating. What do? I enumerate all the subsets with just one element in it. How many of them will there be?
6.
6, 1 for each of the elements. So we go through that. Very good. 1, 2. Remember, it's a subset, so we have to use set notation. 1, 4, 3, 2. 3, 4. 5, 2. And 5, 4. So those are all the sets with one element. Now we have to do all the sets with 2 elements. I'm not going to have room for that. So let's just start out and see what we get. So 2 elements. Well, let's do this the ordered way. We have 1, 4. Whoops, and I 1, 2. And then we have 1, 2, and 3, 2. And then we have 1, 2, and 3, 4, and so forth. Okay. And then we're going to go through and list all the subsets with 3 elements in them. Similarly, we're going to try and enumerate them in an ordered way. Okay. And then all the subsets with 4 elements, then all the subsets with 5 elements. And there's only one subset with 6 elements, and we already have that. That's A cross B. Okay. So even starting out with 2 simple sets, A and B, with 3 and 2 elements, we end up with a power set that's mighty big when we take the power set of the cross product. It has 32 elements in it. Now, how big is the power set of A?
Maybe 8 elements long.
2 to the 3, absolutely. So that's 2 to the 3. And how big is the power set of B?
It'd be 2 squared.
That's right, 2 squared. And 2 squared times 2 cubed is equal to 2 to the 5th. So if I look at the cross product of the 2 power sets, okay, I end up with, what's 2 to the 5th? 32. Is that right? I think so. All right. Are they the same? No. An element of the power set of A cross the power set of B, here's an element of that. The element 1, the single element 1, is in the power set of A, and the single element 2 is in the power set of B. And here's what an element of power set of A cross power set of B looks like. Notice the ordered pairs in this case are subsets of A and B. Okay. All right, let's go on. Here's another practice problem. We're going to count elements. So I have a set A that's got elements 2, 6, 7, 9, and 10. And an element B, that's 2, 3, 4, 9, and 11. And element C, that's 1, 4, 5, 9, and 11. So we ask what is the number of elements in A intersect B, A intersect C, B intersect C. So let's try A intersect B first. What is that set? What's in A and B here?
2 and 9.
2 and 9. Anything else? I don't think so. What's in A intersect C?
4, 9, 11.
11 isn't in A, is it?
Oh,
9
no.
is in A.
Okay. No, it's like empty set. 9. Oh, okay.
Well, 9 is in both. See, 9 is in A and 9 is in C. So it's not the empty set. Is there anything else? I don't think so. And now what is in B intersect C? Let's see.
4,
in both.
4, 9, 11.
4, 9, and 11. Good. Okay, so A intersect B has 2 elements, and A intersect C has 1 element, and B intersect C has 3 elements. And now we need A intersect B intersect C. How would I do that? Well, I can look at that and say A intersect B and A intersect C. What do they have in common?
9.
9. So A intersect. Why can I do that? What rules tell me I can just do that? And that's the same as A intersect B intersect C.
Distributive.
Not quite. Distributive requires 2 different signs. We're just using intersection here. Good try. What we're doing here is actually a bunch of things, okay? What we're doing is we have A intersect B intersect C. So we have A intersect B intersect A intersect C. Okay. So what I want to do is a little bit of, what can we do? We can do a little bit of associative and get something out of it like A intersect B intersect A intersect C. And then we can use commutative and get A intersect B intersect C. And then associative again and say A intersect B intersect C. And what's that equal to? What's A intersect A?
A.
A. So that's A intersect, that's not a U, that's intersect B intersect C. Okay? So that's what's going on there. And so how many elements is in there? Are in there? What do we say? 9
Should
is,
be
is
just-
the element. So there's 1. So now we go back. Whoops, there's
Oh.
1. So now the question is, if I go backwards, how many elements are in A union B? Well, do I have to go compute A union B? No, I can look at that and I use the inclusion-exclusion principle. So the inclusion-exclusion principle says the number of elements in A union B is equal to the number of elements in A. What was that? 5? Plus the number of elements in B, which is also 5, minus the number of elements in A intersect B. What's A intersect B again? It has 2 elements. So that says there should be 8 elements in A union B. Okay. What about A union C? We know there are 5 in A. How many are in B, in C? Sorry, 5 in C. How many in A intersect C?
1.
1. So that means there should be 9 elements in A union C. What about B union C? Well, there's 5 in B and 5 in C, and B intersect C has 3 elements, so we subtract that out and we get 7. Okay, does anybody remember the inclusion exclusion principle for 3 sets?
I think it's the lengths of the individual sets minus the lengths of the intersections plus the length of the intersection of all of them, right?
Yes. What you, the first statement you said was the length. What you mean is you're adding up the number of elements in each one individually. Very good. That's exactly right. And I'm going to let you write that out so we can move on. Does everybody get that? You see that? Okay. So here we have a practice problem using the theorem about equivalencies of sets. Okay. So in this theorem, we want to use it to prove that A union A complement intersect B is equal to A union B. So what do we do? What's the first thing we do? What is your standard friend from everything? Do I have all the same operators here, or are they different?
Different.
So
So
we're
distribute.
gonna need to use
We
distributive
would use
property.
the-
Good job. Distributive. Absolutely. So by the distributive, that's equal to A union A complement intersect A union B. Now what can I do?
negation.
Negation. Yes. By negation, A union A complement is equal to the universe intersect A union B. What's the next step?
Identify. Identity.
I'm sorry, say that again.
Identity.
Identity. Yes, exactly.
Don't you need to use commutative first?
Yes. Oh my goodness. We jumped.
Just curious, would we be docked points if we were to miss saying commutative in this case?
Probably.
Okay.
So that's A union B intersect universal set. Now is the identity. Okay. Good job. All right. Much shorter when you're trying to prove equality in these things, if you can use the equivalency properties, because then you're not having to do 2 element-wise proofs in both directions. Okay. Wow. All right. New topic for today, Boolean algebra. Now, Boolean algebra uses 2 variables, their values 0 and 1. Sometimes people think of them as false and true, 0 and 1. And there are two operators for Boolean algebra, plus and times. And then there's the univariate operator, complement. Now, the basic rules for Boolean algebra are, they look like they're the same as the operators for binary addition and multiplication at the beginning, but they're not the same. So you have that a plus 1 is 1. Why is that true? Well, if a is 0, 0 plus 1 is 1. And if a is 1, 1 plus 1 is 1 in Boolean algebra. Okay. Similarly, a plus 0 is a. If a is 0, then 0 plus 0 is 0. And 1 plus 0 is 1. And that's it for our choices. A times 1 is a times 0 is 0. A plus a complement is 1, and a times a complement is 0. Now, when I do that, you can look at that and say, that's confusing. How can 1 plus 1 equal 1? And it's just got different rules. Okay, when you learn a language, they have different rules than the one you're used to speaking. And that's similar. And if you look, the reason we're covering this in the chapter on sets is that propositions, operators, the logical proposition operators, the logical set operators, and the logical Boolean operators correspond to one another. So if you're given one set of equivalencies, one theorem with all of those properties, you can get all the rest by, well, the logical operator and is the same as the logical, is converted to the logical operator intersection, which is converted to the Boolean operator times. Logical operator or is converted to the set operator union, is converted to the Boolean algebra operator plus. And when you look at that, you can see why 1 plus 1 is 1, because A union B is if it's in A or if it's in B. So that's clearly the case. The logical operator not is converted to the set complement. It's converted to the Boolean complement. And then our special elements of contradiction is equal to the null set is equal to 0 in Boolean. Tautology. Tautology is what? It's always 1 is equal to the universal set and is equal to 1 in Boolean algebra. So you look at that and say, okay, maybe I understand that. So let's just look and just rewrite a logical equivalence using Boolean algebra notation. So what do we have here? Let's suppose A and B are Boolean variables. Then we would say left parentheses, A and gets converted to multiply, not Q gets converted to B complement, or or gets converted to plus, and that's equivalent to A. Dane.
I had a question about operator precedence in Boolean algebra.
Yes.
Is the multiplication operator, does that have a higher precedence than the plus
Yes,
operator?
just the way and an intersection have higher precedence in logic and sets, multiplication has higher precedence in Boolean algebra.
Okay, so we could eliminate the parentheses then here?
Yes, I put them there because it's easier.
Okay,
And
just making sure.
eliminate it.
Thank you.
That is equivalent to saying okay. Let's look at the next one. So not Okay, not says I'm going to make that complement on the outside of the parentheses. And then not P is going to be a complement, and Q, well, that's times B. And that I already have my complement, and goes to times, and now I have A plus B equivalent to A. Now, logical equivalence, if I asked you to carry that forward, you could apply De Morgan's rules to this left, to that left one. You could apply De Morgan's rules. But if you're asked to just convert to Boolean algebra notation, we're done. Okay? Okay. So it turns out, when you look at logic and sets, if you're given the universe U and a set A in U, you can go back and forth to set theory because you can define a predicate P as the set of all X such that X is in A. Okay, that's not set notation. That's the predicate P is defined as, the triple equivalent to says is defined as X is in A. Okay, so now P is a predicate, and we're back to using logic notation. So the logical operators on P of X are equivalent to the set operations on A. Now, similarly, if you're given a domain D and a predicate P of X, you can define a set A. You can define that, let your domain be the universe. You're defining a universe for set theory. And you define a set A that's in U as the set of all X in D for which P of X is true. And a complement is the set of all X in universe such that P of X is not true. So if P of X, what is A union A complement? Well, it's the set of all X such that P of X is true or P of X is not true. So that's the universe, just as you expect. Okay, now unlike sets, in Boolean algebra, there is no minus sign. So what is the set equivalence? Well, you use the set equivalence that A minus B is the same as A intersect B complement. And you convert this right side to Boolean notation if you ever have to do that. So there are two steps in that conversion. So if there's a minus there, remember A minus B is the set of all X in A, but not in B. A intersect B prime is the set of all X that are in A and not in B, because that's what B prime is. Britain, yes.
Can we use that property you just underlined, like in proof by,
Yes.
like an element-wise proof, I mean?
Yes.
Okay, great.
Okay, is that helpful? You could also prove it, by the way, but it's okay. You can use it. Okay. So here's another practice problem. So we're going to rewrite these set equalities as Boolean algebra. So once again, we're going to have A and B are Boolean variables. So how would I write this? I'd say, let's see, A, what is intersect? Well, that's times. Someone asked, do I have to write the dot or is it the same without the dot? And the answer is it's absolutely the same. I write the dot in case it's unclear without it. That's all. You do not need to. Left parentheses, B prime, okay, that's B complement. Union, oh, union converts to plus A equals A. The next one looks more complicated. So now remember, we're not proving anything with this problem. We are doing straight conversion. So let's do a straight conversion here. Left paren, A plus B. So union goes to plus, intersection goes to times. A complement, well, that's just Boolean complement. Intersect is times C. Complement is equal to A plus B times C complement. Okay, now we're going to use our statement here. So what is that equal to? That's equal to A intersect B complement. Complement equals to the right-hand side. Okay, so what do we say? Well, left paren, A times B complement. Complement equals A complement plus A times B. Are you guys getting the hang of it? I can't tell. Are you not getting the hang of it? Still can't tell. Okay. Well, this is a straightforward conversion. Okay, let's look at the equivalencies and whip through a few of them. So if I have the commutative, what is that in terms of the commutative for multiplication and addition? What is that in terms of Boolean variables? Well, it's A times B is equal to B times A, or A plus B is equal to B plus A. Okay, let's try the identity here. So A times 1 is equal to A, and A plus 0 is equal to A. Remember, the empty set, the null set gets turned into 0, the universe gets turned into 1. Okay. Negation, A plus A prime is equal to 1. A times A prime is equal to 0. Okay. I had more of them, but I'm not going to go through all of them. Okay, we can go through every single one of them. The complement and negation, we just convert directly. That doesn't have two sides to it. Okay. Let's do a proof with Boolean algebra. Oops, let's not do a proof with Boolean algebra. Let's take our 5-minute break. You got till 11:34. I can answer any questions anyone has or any issues you want to raise. Now's a good time.
I had a question.
Yep.
So I was doing the homework problem and it asked us to describe a set. Can we describe a set using a recursive formula?
That's
Or-
not usually used for sets.
Right. So we should probably use the closed formula then.
Yep.
Okay. This is just something I was curious about because I didn't really find it in the textbook or anything.
Yeah, that probably means it isn't usually done.
Yeah. Okay. I just wanted to double check.
No problem.
Professor, I have a quick question for the homework.
Sure. Who's asking?
Yes, for the power set, do we need to identify each element in the power set, or we can just give the number of the set?
It depends on the question. I don't have them in front of me.
Okay.
It depends what the question asks. If it asks you for the number of elements, then you can give the number. If it asks you to find the power set of a set, then you have to list the elements. You have to use set notation, set builder notation, and list the elements of it. Is that helpful?
Yes.
Good.
I also have a question about the homework.
Yes.
So question 7 is asking you to prove if the set of n squared minus 1 intersect 2m is a subset of 4k.
I'm sorry. 4K is not a subset. It's an element. What do you?
Okay, it's a set containing all numbers equal to 4k.
Okay, and then I need to repeat the problem correctly so I understand it, okay?
Okay, so it's asking for us to prove that A intersect B is a set of C, where A is a set of all numbers that are equal to n squared minus 1.
Yep.
And B is a set of all integers 2m equal to 2m. And then C is a set of all integers equal to 4k.
Yep.
So I know how to do this if it was a union question. But the problem is I'm having a hard time figuring out how to link set A and B together so that I can prove that that is a subset of C.
Are there any elements that are in both? You're asked to prove the intersection. Intersection
Yes.
means you have to have an element that's in both of them.
Mm-hmm.
So are there any elements in it? What would the
believe
properties of an
so.
element that would be in both of them be?
Well, they would both have to be even because set B is all even numbers. So set A would have to be all
And
basically
set A is all n squared minus 1 where n is an integer. So
yeah.
So we're asking about the set of elements in the intersection of A and B.
Mm-hmm.
So that means they have to have both properties, and that should be a good starting point for you.
Okay. So basically
Any more
X
than
has
that, we
to
should
equal
go-
both
Any
of
more
those.
than that, we should go private.
Okay.
Okay, so you can send me a note in Piazza or something, okay?
Okay.
I already got the idea. Could I try to do this one?
Good, I think we're ready to start. We're actually over. When you're doing the dual of a logical equivalence to Boolean algebra, you can go directly. Remember, you have equivalences of all these logical operators. Logical operator to Boolean operator has its own equivalence. You don't have to go through sets. You can go immediately from logical to Boolean, just the way we did in the example a few times back, the practice problem a few times back. Okay? Here we're asked to prove that A plus A times B is equal to 1, where A and B are Boolean variables. So let's do that. Let's say, what is A plus A times B? Well, A is A times 1. How do I know that? What property?
From the identity.
Good. The identity. Very good. Now what can I do?
We could do the absorption.
Oh, well, we could. You're right.
I would do distributive first.
Thank you. I like that better. That's distributive. Now what do we do? What's B plus 1?
1.
Why is that?
From the universal bound.
Very good.
Did you miss the commutative step for 1 plus b?
Oops, was I supposed to change them around?
It's supposed to be
Let me look at universal here.
Yeah.
Yes, you do. Equals A times B plus 1, commutative. Okay, now we got universal bound. And that's equal to A. Why is that equal to? No, that is not. Did I copy this problem down wrong? Yes, I did.
That's what I got too.
That problem, that's wrong. That's equal to A. Whew. All right, and why is that true? That's identity again. I do try on the problems I give you to work them out completely ahead of time to make sure I don't make that mistake. Good. Okay. Let's do another one. Simplify the Boolean a plus b, the quantity a plus b times the quantity a plus c, using the equivalencies in Theorem 6. So what's the first thing that we're going to use? What's the first thing we're going to do?
Distributive property.
I'm sorry, say again?
Distributive.
You know, you could do the distributive property. I like that. What would the distributive property be?
Quantity a plus b times a plus quantity a plus b times c.
I'm sorry, I missed that. What's the distributive property say? The dual distributive property. Let's do the dual distributive property first. We had a times b plus c is equal to a plus b times a plus c. Does that look familiar? That's a distributive property, right? What do we have here?
Excuse me, I think that's not correct. The distributive is the a times b plus c is equal to a times
plus
b
c.
plus.
You are so right. Wow.
No, not all that is a times b plus a times c.
Good. I like this. A times b plus a times c. Good. What's the dual of that?
Yeah, and there have two
The
branches.
dual is a
Yeah,
plus b times
times c. Yeah.
And that's equal to a plus b times a plus c.
Yes.
Okay. Now does it look familiar?
Okay.
What does it look familiar? Now it looks like I have a times b times a plus c. Is that right? So we have a plus b times c. And what did we use? We used the distributive. What's practice problem 6 again? A plus a times b is a. Do we have that here? Nope, we don't have that at all. Okay, good. Okay, let's go on. So the duality, I just gave you an example of the duality for Boolean algebra. Just as we have a duality for sets and a duality for propositional logic, we have a duality for Boolean algebra where we interchange plus and multiply and interchange 1 and 0 as with sets. As with sets, we leave complement alone. That is totally unchanged. Okay, so suppose we want to form the dual of the expression a plus 0 all complement times the quantity b complement times 1 plus a. So what do? We say, okay, let's give it a whirl. We say a plus 0 complement b complement times 1 plus a is equal to, now here's our change. We have an a times, what's the complement of 0? 1.
1.
Very, very good. Prime complement. I have a multiply there, so that goes without the dot, but it's a multiply, so that becomes a plus. And then I have b prime, and then I have a multiply, so that's plus. Now there's 1, but what's its complement? What do I change it to? I change it to 0. Okay. Times a. Now I do need the parentheses because I don't want to change the order of operation. So I did not need parentheses around this one because plus has a lower hierarchy. But I do need it when I change the order of operation. Okay, well, what is that? Let's just carry it on a little bit further. A times 1 is a by the identity. So we have a complement plus b complement plus 0 is b complement. That's by the identity. Let's say a times a, yes. Okay. If I want to keep going, I can say, well, commutative property. So what is a times a complement?
Zero.
Good, 0. And then this is by negation, I think. And a, then we end up with, and that's the identity, the plus identity. And that's the simplified form. Now, do you have to do that? Nope. This was the step that all you had to do for finding the dual. But we carried it on and simplified the dual as well. Okay?
Professor, a quick question.
Yeah.
If we're on an exam, can we add any amount of parentheses that preserves the order of operations? Is that okay to do?
You sure can. Parentheses, well, if any number, I mean, let's be careful. If you add 10 when you only need 1, that's a little excessive and makes it harder to read. So you can add whatever you think you need, okay? But if you only need 2, if you add 3 just to be sure, that's okay. But if you add 10, not so much, okay?
That's clear, thank you.
Okay. Prove that if a plus b is equal to b, then a plus b times a complement is equal to b. Am I? Okay. So do you guys want, why don't you guys start this and then give it a try and then we'll prove it. I'll tell you one thing we start with. What do we always start with? Proof. suppose A and B are Boolean variables such that A plus B equals B. I started for you. Now you keep going. Okay. What's the next step? Somebody give it a try and tell me what you did.
I said that A could equal 0 by the identity property.
Tell me why.
Because the identity property is that, I guess we need the commutative property to switch the order.
Yeah, but it could equal. That's true. It could. Let's see. Well, tell me. So you said that means that implies that A equals 0. Why is that?
Because the identity property is that a Boolean variable plus 0 is equal to the original variable.
Well, yeah, but is that the only way we get it?
I could be wrong, but that seems like just a direct application of the identity property.
Yeah, but you're starting out saying A is 0 because of that. Okay. One of the ways to deal with it is true if A is 0. The question is that the only time it's true? See, this doesn't say that B could be 1. And if A is 1, then 1 plus 1 is 1. Okay. So Boolean algebra is not quite the same. So that doesn't say A has to be 0. It can be true if A is 0, but A may not be because we don't know what B is. Okay.
That makes sense.
Okay. So that's a little too short. Good try, but not quite enough. So let's look at B. B is equal to A plus B. That's given to us. Okay. So if that's the case, then that's equal to A plus B times 1 by the identity. And what else is equal to 1? You had the right hint. What about A plus A complement? That's also always equal to 1. What's that by? What's that one called? If I remember my rules. Now what do we apply? We applied the distributive property where this is considered to be a single variable, and we apply it on this summation. So then we get A plus B times A plus A plus B times A prime. Okay, commutative then says, what was that? That was distributive. Now, commutative says that's just A times A plus B plus A prime times A plus B. Okay, what's that equal to? What's that equal to? That's equal to A by absorption. That's absorption. What's A prime A times A equal to? By the way, this was distributive again. Okay, what's A prime times A?
0.
0. And then we get to our final state by saying that's the same as A plus B A prime, and that's commutative again. And this is by negation, I think. And we have a question. We had a question from somebody who disappeared.
Oh yeah, that was me.
Do you still have a question?
Yeah, so I was just kind of wondering, because I noticed that you started from the left-hand side of the implication.
Yeah.
But the way that I did it is I started from the right-hand side. I did distributive to do A plus B times A plus A prime. And then I noticed that A plus B showed up in there, and then I replaced that with A. Would that still be a valid proof?
Okay, you said A plus B times A prime is equal to A plus B times A plus A prime.
Yeah.
And what is A plus A prime?
That's 1. And A plus B is also equal to B according to the implication.
Yours is shorter. I like yours better. Very good. Not only is it okay, it's very good. Of course, you have to fill in, which I did not write. This was the distributive. Right, you are, and this was in negation. No. It's, I never get that right. Which is why I give you the rules. It is negation. What do you know? Negation. And that's the identity. And yours is better. Grant.
Does it matter that in his way of doing it that you're starting on the right-hand side after the then statement?
No, because then no, that's perfectly fine. You're not he did not start by saying, suppose this whole thing is true. He said, well, let's see what that is equal to. And that's perfectly good. Is that clear?
Yeah, that's clear.
He didn't assume the conclusion. He took the left side and then showed it was equal to B. Okay? Fred.
Yeah, I just want to see, we already use the negation to get the A plus B times the A plus not A. So we can just apply the distributive to get the A plus B times the A, not A. Like the upper one, the top, we got it.
I'm not sure I understood what you said. Could you tell me, could you write it down and tell that to me, or in the chat or something? Because I didn't exactly understand.
Okay, hold on.
Okay, I'm sure you're right, but it's helpful if you can write it down.
I think what he's talking about is in your proof, right
Yeah.
after you did negation, doing the distributed law, you transferred it in. Instead, why couldn't you just pull out the A and it would be A plus B times A naught, or complement, sorry.
Are you talking about here?
Yeah. No, last one.
This one?
Negation, yeah. We can get the answer, just use distributive. And then
Well, I did use the distributive.
not from the left to hold on.
Oh, you want to do it the other direction?
Yeah,
Yeah, that's okay too. Perfectly fine.
yeah. I think they can
No,
save
if you
more.
want to do it the other direction, you actually have to use commutative first and put this on the left side. But the idea is perfectly fine. So we now have 3 different ways to do it.
Yeah.
David, yes, your question.
Yes, I have a question regarding the last step, because we have A plus 0 plus A prime B.
Yeah.
Well, I think we need the identity. Yeah, because we have plus 0.
Yes. So, well, the A times A gave us 0. And then before we do the commutative here, we have the identity and commutative. You're absolutely right. Thank you. Good job. I like when you guys fill in the blanks. Good. Okay. I'm trying to figure out why what you wrote, Fred, is correct. What did I miss here?
Here.
So you have absorption with the, well, you forgot the commutative. So you take a commutative line and then you say, well, that's equal to A. Yeah, you can, but you have to do commutative and you left out a bunch of steps that should be there. But otherwise, that's a good approach also. Okay. I wanted to do one more problem. You think we have time? One more. Okay. We're going to do a proof by contrapositive. To remind you, we need proofs by contrapositive for sets. If A and B are sets, prove that if A is contained in B, then A minus B is empty. Okay. So if we're going to do that, what is the contrapositive? Well, the contrapositive is if A minus B is not empty, then A is not contained in B. Okay. So how do we prove that? We say, well, suppose it's not empty, then X in A minus B means X is in A and X is not in B. Okay, by the definition of subset, A cannot be a subset of B. Done. That's a quickie. Okay, sometimes the contrapositive is really good. So that's element-wise, but it's a real quick one. Are there any questions?
So I wondered with element-wise proofs, the text always starts with something along the lines of let A and B be sets given such that, do we need to start our proofs with that kind of?
Yeah, well, you're saying let's let A and B be sets such that the hypothesis holds. Okay. And it's useful to do that. Okay. Then you usually say, if you're saying that if you've got something that says some expression of sets is a subset or equal to another expression of sets, you always start out and say, let X or Y or whatever be an element of the one that's supposed to be the inside, the subset. And then what does that mean in terms of, if it's an intersection or union or whatever? Then you sort of say, well, let's see, that means the following, and go through what that means. All the while thinking about what you have to show it's a subset of. Okay? Grant.
I was actually just wondering if you know what day the test
We'll come
grades
back.
are going to be released.
Yeah, the tests are delayed. The exams handback are delayed because I have to finish dealing with the cheating issues. And that means I can't hand it back to anybody. So I should have them back to you. I don't think I'll be done by tomorrow, but I should be done by Monday and you'll have them then.
Okay, thanks.
Okay, they are completely graded, but I can't hand them back until we finish dealing with this. I'm sorry. Please, people, do not cheat. I really like giving you good grades, even earned grades, but I hate it when you cheat. Silas.
I had a quick question about homework 3.
Can you speak a little louder, please?
Is this good?
Oh, you're still super quiet.
Silas. Question about homework 3. Okay, what is the question? Silas? Will we, well, if you say in logic that, if you say let PQR be Boolean variables, you won't be docked. How's that? Okay, he's asking if you have to change the variable names. If you're given logical variables, PQR, and want to convert to a Boolean expression, do you have to change them to like ABC? And my answer is, if you say let PQR be Boolean operators, Boolean variables, then it's okay. Any other questions? With that, I will see you Tuesday. Have a good weekend. Get your homeworks in. Don't copy from anyone, please. Get them done. If you have any questions, there's still office hours today. There are office hours tomorrow. They're in fact office hours tomorrow. They're from 5 to 7, which is unusual on a Friday. So if you need them, they're there. Okay. Do well, please.
Thanks.
Bye-bye.
Yes, thank you.